In this series of lessons on flight mechanics, you'll be studying the forces acting on an aircraft in flight and the response of the aircraft to those forces. For an aircraft to be in steady, unaccelerated flight, the following conditions must exist. Forces acting downwards must exactly balance the forces acting upwards, and the forces acting backwards must exactly balance the forces acting forwards. In addition, the sum of all moments must be zero. When all these conditions are met, the aircraft is in a state of equilibrium. In straight and level flight, there are four forces acting on the aircraft: lift, weight, thrust and drag. Weight acts through the centre of gravity, the CG, vertically downwards towards the centre of the Earth. Alternatively, weight can be said to act parallel to the force of gravity. Lift acts through the centre of pressure, CP, normal or at 90 degrees to the flight path. Drag acts backwards, parallel to the flight path. And thrust, for the purposes of this lesson, although not strictly true, can be said to act forwards, parallel to the flight path. For an aircraft to be in steady level flight, a condition of equilibrium must exist. This unaccelerated state of flight is achieved with the aircraft trimmed with lift equal to weight and the throttles set for thrust to equal drag. For steady level flight, then, the opposing forces must be equal. The proportion of the lift force to the drag force, known as the lift-drag ratio, for most modern aircraft is between 10 and 20 to 1. In simple terms, this means that lift is 10 to 20 times greater than drag. The lines of action of thrust and drag usually lie fairly close together, so the moment of this couple is small and will be disregarded for this study. The positions of the CG and CP are variable, but under normal circumstances will not be coincident. The CP will move forward as angle of attack increases, and will usually stay aft of the CG, unless the design allows the tailplane forces to stabilize the moments adequately with a forward CP. The CG will move as fuel is used, usually forward, but will usually, on conventional aircraft, remain in front of the CP. The function of the tailplane and elevator, or the stabilator, depending on the design, but referred to generally as the tailplane for simplicity, is to maintain equilibrium in pitch by supplying the force necessary to counter any moments resulting from CP and CG movement. With the CP providing a pitch down moment being behind the CG, the tail surfaces must provide a down force. If the tailplane is producing a balancing force, this will add to or subtract from the lift required to balance the weight. For a down force, the usual situation, lift must equal the weight plus the tailplane down force, and for an up force, lift must equal weight minus the tailplane up force. For steady level flight at a constant weight, the lift force required will be constant, and at a steady speed, the wing will produce this lift at a given angle of attack. However, if the speed is changed, the angle of attack must change to maintain the same lift. As the lift changes with the square of the speed, but in direct proportion to the angle of attack, the angle required for constant lift will vary as shown on the graph on the screen. The minimum possible level flight speed, Vs, for any given lift force is achieved at the critical or stall angle of attack. For steady level flight at a constant speed, the thrust must equal the drag. Drag increases with speed above minimum drag speed, VMD, and so to maintain a higher speed, the thrust must be increased by applying more power. To fly the speed at point A requires a thrust of T1. And to fly at speed B requires a thrust of T2. If the thrust is increased to T2 when the aircraft is at point A, the thrust will be greater than the drag, and the aircraft will accelerate in proportion to the excess thrust AC until it reaches point B, where the thrust and drag are again equal. If T2 is the maximum thrust available, then the speed at B will be the maximum speed achievable in level flight.